Colleagues, dear Vice Rector, it's my great pleasure to welcome you to our 12th International Symposium of Cognition, Logic and Communication. This year's topic is the impact of visuospatial skills on learning. And before saying a couple of words about the symposium, let me give the floor to the Vice Rector for Exact Sciences, Life and Medical Sciences, Professor Valdis Segliņš.
Dear Chairman, organizers, distinguished guests and participants, welcome at the University of Latvia. You are like early birds for the celebration of university 100 years. We are very soon. And sure, during this time, we become more conservative, more traditional. We have 13 faculties and number of institutions around, and at the same time, we can't be old and never. For characteristic, probably the better word is the composite materials, where besides the traditional values, there are much more new things, and like in this aula, or big hall, there is elements of this Art Deco or Jugend style. Besides, there is a number of things from the early 30s, like a balcony, and the gypsum marks from 50s, and probably somebody recognize some modern things around, like our faculties as well. There is, besides the traditional science and interests of the research, there is some new grounds as well. But for the small country and for the small population like in Latvia and let's say medium size for Europe, university like ours, it's around 15,500 students. It's not a way on conventional development stepwise. We need much more speed up, and when the traditional and well-recognized business and management faculty and interests reach computer science, advanced and fast-growing, beside the cognitive science, there can be cooked something totally unusual, something new which breaks down traditional barriers, traditional borders between, and there is a lot of things to be learned, much more to understand, and from the university point of view, it will be very useful if there are, from your symposium, be outcomes not only on learning and the results, but the subjects for the teaching. We should change society. We should much learn before what we developed, what we recognized, what we found out, but much more how to teach the others, to not make a distance between the, let's say, usual and unusual scientist. It's a subject and it's a task for universities, and I'm very happy to see all of you here for your very important and interesting symposium where, besides the lectures, which probably change our minds, or at least change our look on things, followed up by 3 workshops, which be open doors, and the interest of outcomes are very high. Thank you for your coming. Thank you for organized untraditional things in very traditional university. Thank you and good luck for all of us.
Thanks to Professor Segliņš. It's a nice words. Okay, so now I'm also pleased to give the floor to one of the co-organizers of the symposium, the Dean of the Faculty of Business Management and Economics, Professor Gunārs Bērziņš.
Dear Chairman, distinguished guests and participants, it's my great pleasure to see you all here and in this conference, which is a new subject for our faculty. Traditionally, business management faculty is not considered to be in the cognitive science, but nowadays things are changing, and this conference is one of the change indicators, I would say that way, which brings together fields of studies more and more. And I strongly believe that future is in this collaboration between different fields, especially nowadays when computer science, artificial intelligence is how to say, more interlinked with very different subjects. For example, our researchers in decision-making or engineering decision-making are publishing in conferences on artificial intelligence because business decisions on very day-to-day things we are used to be, for example, the ticket prices or discount prices, or when we have to change different parts in the car, basically are all algorithmic-based decisions. And now we have come here to the question, how do we put statistics, mathematics, and cognitive science together? And I strongly believe that this conference will show us the way how to integrate our fields of knowledge, how to see our traditional fields in different light, and it will be great added value. And I'm for this, I wish all of us during this conference this added value to find different angles of views to our traditional thinking and traditional problems we try to solve. And I wish you a great conference, great new angles of knowledge, and great speeches. Thank you very much.
Thanks, Professor Bezinc. Before starting our first keynote talk, which is simultaneously Accenture MedScience talk, let me say a couple of thanks. First of all, we are thankful to our sponsors and supporters, software company Accenture, for supporting this event. Accenture is a leading Latvian software company supporting MedScience lecture series and also co-organizing highest level international scientific exchange among multidisciplinary areas and researchers. Many thanks to Accenture. The project is also supported by the patron of University of Latvia, Mikrotīkls Ltd. The nation is administered by the University of Latvia Foundation. Many thanks also to the International Relations Department of the University of Latvia. And finally, thanks to co-organizers. The symposium is co-organized by the Faculty of Computing and Faculty of Business and Management, and Economics of the University of Latvia. And let me conclude by saying that it's great to see you all here. And on behalf of the Laboratory of Perceptual and Cognitive Systems at the Faculty of Computing, let me wish you a great day with lots of discussions, interaction, and lots of inspiration during this day. And now we are ready for the opening keynote, which is at the same time Accenture MedScience talk. And I'm pleased to give the floor to Professor Mark Steve from Chicago, who will introduce our plenary speaker, Professor David Uttal. Thank you.
Thank you. My name is Mike Stife. I'm from the University of Illinois at Chicago, and I have the honor of introducing the first speaker of today, Dr. David Uttal. It's my great pleasure to introduce David. 17 years ago, he was actually a member of my dissertation committee, and as intimidating as that was, it's nothing compared to having to introduce him as an adult academic at an international conference, but it's my great pleasure. David received his PhD in developmental psychology from the University of Michigan, and he's currently professor of psychology and education at Northwestern University. David's the recipient of numerous awards for his work, including appointments as a fellow of both the Association for Psychological Science and the American Psychological Association, in addition to just coming off his term as the president of the Cognitive Development Society. David is the author of more than 90 research publications and the winner of more than $10.5 million in research funding alone. He is an expert in human spatial cognition and has a distinguished record of contributions in this area, particularly with regard to his groundbreaking work on how children develop their symbolic knowledge using concrete models, as well as their abilities to interpret and make use of spatial information that are in maps across the developmental trajectory. Today, he talks to us about when, how, and why does spatial thinking matter in learning science and mathematics. I've followed David's work very closely in this area, and I can say that he has been a major contributor in helping us think very critically and carefully about the role of spatial cognition in learning and in professional practice, and I'm sure you'll enjoy his talk today. Please join me in welcoming David Uttal.
Thank you, Mike. Never thought after 17 years we would be in this position. I'll save my jokes about Mike for my introduction later this afternoon. Thank you to the Dean and Rector and Professor Schilters for their invitation here. It's a joy to be here, and also to Accenture for the Mad Science series. I'd like to begin with some puzzles. Where on earth can you walk 1 mile south, 1 mile west, and 1 mile north, or it could be kilometers too, and end up exactly where you started? Do we have an answer? Don't be shy. As soon as I say it, you're going to know. It's the North Pole. Here's the proof in visual form, which Rob will talk to us about. And here's another question. Do frogs have lips? Actually, I don't know the answer to this question. I mean, it depends on what your definition of lip is, but they have some kind of... Now, the answer doesn't really matter. What matters is the process, the mental process that you use to try to come up with these answers. You almost certainly evoked some sort of representation that captured at least some of the elements of the object as if you were looking at it. And we now know that some of the same neural circuitry is activated in imagination that is activated in actual vision. So there's this tight coupling in the brain between vision and imagination. And this is what we mean by spatial representation, something that captures something about the relations. It's not the same. If I asked you, for example, do humans have lips? You don't have to imagine the face. You know this is a fact. If I ask you about frogs, then it's a very different kind of thinking because you don't know and you have to imagine. Now, the reason I'm talking about spatial intelligence in this forum is that it's extremely important for performance in what we call STEM, science, technology, engineering, and mathematics disciplines, including the following. At least in the United States, this is a dramatic problem, and I think it's a problem all over the world that students struggle with this, and yet we need for them to succeed more than we ever have before. Many students begin with great enthusiasm, both men and women, but many drop out, if not before college, then early in college. And we want to understand why and prevent it, and also to increase women's participation to make it more equitable. And all of these factors involve, we think, one important skill behind this is spatial skill. So all I mean by spatial cognition is thinking about locations and the relations amongst them, as opposed to word semantic facts. Now, as examples of the importance of spatial thinking in science, consider some well-known examples from the history of this case in chemistry. One is this tale. It may or may not be true, but it does accentuate the point that Kekule, in coming up with the structure of the benzene molecule, dreamt of a snake biting his tail. Now, the structure is actually not a circle, but rather hexagon, six-sided. But what was critical was the dream about the ring. And that was the idea. And this is, as Mike, I think, may talk about, that one of the first insights into structural chemistry, into how organic molecules were built, not just what they contain, but their spatial structure. This was a founding discovery of organic chemistry. Perhaps 100 years, 80 years later, Crick and Watson discovered the structure of the DNA molecule. And again, it is described as a particularly spatial insight. In fact, in their paper, they say, we wish to put forward a radically new structure for the DNA molecule. And this sense of radically new, that it was an insight, a discovery, it was as if they were seeing something for the first time, which they were. And of course, we all know what all the important discoveries in science and medicine that have followed from this structure. But it's not just, these anecdotes are important and interesting, but that alone is not enough of a reason to invest. They're good stories. They may well reveal something, but we need hard data. And fortunately, John Way and his colleagues have looked at data from over 100,000 American high school students. And what's so interesting about this is it began in 1960, testing 100,000 representative students of the whole country. And then they've been following, and in fact, they still continue to follow them. And so we can look at where they ended up, what careers did they take. So this is career occupation at age 33, when they were tested at approximately age 13 to 17. And then we follow them for 20 years, and then all the way out now, they're still going to their high school reunions and tracking them down to the extent that they can. And they found some very interesting relations between different kinds of mental abilities and where people ended up. So in these original tests in 1960, they measured many cognitive abilities, including math, verbal, and 2 forms of spatial ability. And this turned out to be critical, because what this diagram shows you is the X and Y axes are easy. This is 0 would be an average score, and this is standard deviation units above or below the mean. The arrows are a third dimension representing the sort of added effect of spatial skill. How much more do we know about where people went in their careers if we know the spatial ability score? And the answer shows, particularly for science and engineering, as well as for business. Business is a negative prediction. Those with relatively low spatial ability went into business, but those with relatively high spatial ability tended to go into science, mathematics, and engineering. And you can see that for some forms of engineering, spatial skills were more important than verbal or mathematics skill. So it's actually the best predictor. And this remains true in more recent studies as well. You can sort of sum up the data in this way. This is just those arrows. This is just the one dimension. It's saying how much more predictive power do we get if we look at spatial skill over and above mathematics and verbal. And it really matters for starting, interestingly enough, visual arts, which I was discussing last night, physical science, math and computer science, and particularly engineering. Spatial skills really matter. So these anecdotes are important, but we have hard data. But unfortunately, spatial thinking isn't presumed. Thinking is presumed throughout the kindergarten through 12th curriculum, but is formally and systematically taught nowhere. This quote's about 10 years old. I'd like to think things are changing a little bit, but still, the situation is not particularly good. We assume spatial reasoning, but we don't teach it. And one of the main themes of my talk today is that it can be taught, and teaching it has benefits. We don't expect people to learn to read without instruction. Some children pick up some elements, but it seems like some degree of formal instruction is almost a requirement for literacy, and almost all societies provide that for their children. We don't do that for spatial thinking, and I think we should. Perhaps this is the tyranny of the printing press. Bob was talking last night about the tyranny of the typewriter, that we think in linear ways, we think in words. This was an extremely transformative event in human history, the inventing of the printing press. It changed what it meant to be intelligent. And I think perhaps spatial thinking went by the wayside when words and press and print became the primary way of thinking and communicating. The question I want to ask today is, why is spatial ability related to STEM? And I want to consider some alternate models. It's very important that we be as specific as we can. Neither Mike nor I believe in a magic bullet. We both believe spatial thinking is very important in STEM, but we don't believe that you can simply enhance spatial thinking and everything will be cured. It's not quite that simple. We need rigorous skeptical thinking about when and why spatial ability is related to STEM. So one common explanation that that I think both of us would refute is that STEM is a highly spatial field, and so you need high spatiality to do well. After all, a geologist, for example, needs to be able to mentally undo the transformations that led to these folds and faults in these mountains to explain their origin. Chemistry students, we know, need to be able to think about spatial rules such as chirality. This simple difference makes a tremendous difference in the properties of the molecule. Even though they contain the same basic elements, they may behave differently because of their spatial configuration. So these are important. So we may say, okay, STEM is really spatial. You need to be high spatial to succeed in STEM. It would be nice if it were that simple, but it actually isn't. And we know it isn't because we look at data that suggests a really interesting fact, that as you move through STEM, become more advanced, spatial ability actually becomes less predictive. And that may seem like a paradox. Didn't you just tell us that it's highly correlated and now you're saying it's unimportant? What's going on here? Well, I want to resolve that paradox and explain how both can be true. As you become more expert, more advanced, an expert spatial thinker like Mike in chemistry, you actually use spatial ability less because domain knowledge becomes really important. As you learn more about chemistry, you actually have to do less spatial cognition. But very importantly, at the beginning, we rely very heavily on spatial abilities, and so it provides kind of a bottleneck that we can help students get through. So let me consider a few scientific domains: geoscience, chemistry, dentistry, and physics just a little bit, to show where the same sort of pattern seems to hold. The best study that I think illustrates this is by Zach Hambrick and his colleagues, and the reason I say it's the best is because it involves actual, real geological practice in the field with experts and novices. At least in the United States, geology training almost always involves field trips, where they, rather than just study from a textbook or a computer, it's seen as extremely important to go out into the field. This is data from Michigan State University, where students go after their second year to the western United States, and they have to perform these real geological tasks. Geological mapping involves making inferences about what is below the Earth based on what you observe above the Earth, and then mapping that out. So this geological map shows what kind of rocks are under the surface, based in part on inference about what we see above it. And what Zach and colleagues looked at is the relationship between spatial ability and the ability to make these maps. And importantly, they were able to look at both low and high spatial ability students. Believe it or not, there are some relatively low spatial ability geologists, and he was able to compare how spatial ability affected the performance of experts and novices. And what you can see from this result is that spatial ability matters greatly for the novices, those who are just beginning. So if you have low spatial ability, you perform relatively poorly. However, if you have high geology, it should say, high geology knowledge, spatial ability doesn't seem to matter at all. There's no difference statistically between these points. And he suggested that knowledge about the particular field allows us not to rely as much on sort of raw spatial abilities. If we have to visualize and mentally transform things all the time, it's very cumbersome to do so. But we know as experts what to look for and focus only on what is relevant. Here's some work that's from Mike's dissertation, all 400 pages of it. This was excellent. You all know the classic mental rotation task where you're asked to make a judgment about whether a stimulus is rotated or a mirror image, inflected. Does everyone know this task? So, for example, if I say, is this a rotated version, the same, or is it different? If it's a mirror image, no amount of rotation can move it into this orientation. But if it's simply rotated, then you can move it into this orientation. So here we would say same, and here we would say different. We've known for a long time that the correlation between the amount that you have to mentally rotate it and reaction time is very, very strong, well over 0.9. And this has been used as evidence that students or people mentally rotate it. So if I see this in 300 degrees, well, I might either rotate it this way or this way. The more rotated it is, the more time it takes. And this is one of the first sort of cognitive psychology demonstrations that we can infer mental process on the basis of behavior, in this case, reaction time. Now, Mike, in his dissertation, did some extremely interesting studies using both quantitative and qualitative methods, where he looked at expert and non-expert chemists, making judgments about chemically relevant diagrams and generalized irrelevant diagrams. These traditional mental rotation intentionally uses objects that are meaningless, that have no expertise. There's no expertise in rotating these blocks. There is expertise in making judgments about the structure of molecules based on this. And what Mike found is that there's a very interesting difference in that the experts for the symmetric molecules make the judgment very quickly because that is part of their knowledge of chemistry. So there's no reaction time, no matter how rotated it is. They're very fast, and the line is flat. But the experts are just the same as the novices for these kinds of stimuli. So do you see what's going on here? Expertise makes a real difference. It's suggesting there is some sort of different process going on, and Mike will tell you more about what exactly that process is. But again, we see that spatial skill might not matter as much for the expert as it does for the novice. So as an interim summary, we can say that there's strong, convincing correlations of a relation between psychometrically assessed, that's like paper and pencil test, of spatial ability and STEM attainment, how far you go. There's weak, inconsistent correlations between spatial ability and expert performance. So it can't be that spatial ability matters simply because STEM is highly spatial. That explanation can account for the data. What does? Remember now, we're trying to explain these correlations. We're trying to explain why spatial ability matters for who goes into these things. This is only talking about who ended up in those professions. It's not talking about what they do in their everyday performance. So it's quite possible that something in their relatively early education could have selected them into these professions, even if it becomes unimportant as they go through. And I think that's the critical role of spatial ability, is that it may be a gatekeeper, that it keeps people getting through, like introductory chemistry. I'm very fond of saying that introductory organic chemistry is the largest source of psychology majors, meaning they drop out and they come knocking on my door and they say, I want to be a psychologist because I don't like science. I'm like, oh, please don't say that. That hurts. And this is a good example that spatial skill might be keeping those people out of science and putting them into psychology. So what I'm proposing then is that spatial abilities are sort of a limit on who can get into STEM. If you can get through this introductory period, then you might be able to succeed, as the geologist in Hamburg's study did. So it's what we call a catch-22. You can't succeed with it, but you can't get there without success. So how do we break this problem? And this is consistent with the data about when people drop out. So there's a lot of what we call the leaky pipeline out of STEM, that many people leave relatively early in college. If you can make it through the first couple of semesters, then this is showing the probability of dropping out. It's modeled as if it was like dying. It's a hazard. And when do you drop out? And most of the dropout occurs right after the first year, in the third semester. And I would say that some of this, and we have some data to support this, is the low spatial ability students, and then they go on and they can succeed if they got through the initial year or two. So what can we do about this situation? If this is why spatial ability matters, what can we do? And for the rest of my talk, I'd like to consider two possibilities. One is spatial training, which means we try to train people to think more spatially by enhancing their basic core abilities. Not because it's a magic bullet and it's going to cure all of our problems, but because it may help them get through the critical early parts of the curriculum. So this would involve improving basic skills, such as the mental rotation that I talked about. It's not a magic bullet, but it's specifically to get students through initial stages. But I'm also going to try a second approach, which is sort of more higher level, top down, if you will. In education, there's a lot of debate about whether this kind of basic training transfers to other skills. Transfer will be the subject of my workshop this afternoon. And lots of times it may not. And so I think we need both approaches. This means more about teaching spatial thinking as a habit of mind, not just about rotating abstract, meaningless objects, but using spatial tools to solve real science and engineering problems. And so I'd like to talk to you about both lines of research because I think they're complementary, and in fact the data are starting to... I didn't say anything that radical. Is that a fire alarm? Maybe it's a fire alarm? Okay, if it is, let me know, we'll exit. Okay. So we could approach science and engineering from a spatial perspective. And so my evidence for the malleability of spatial training, that it can help, comes from an extensive meta-analysis of about 220 studies of spatial training across a variety of fields. So we put together all the literature we could find for about 40 years of various experiences that people have had, either formal or informal. By formal, I mean there was specific training. Somebody said, I want you to learn to do this. By informal, I mean something that occurred in their everyday lifetime, such as they like to play video games and they played a lot of them. Or even they took a job, such as clothing design, that required a lot of spatial skills. And so we put these all together into one massive meta-analysis where we look at the effect of spatial training across many different kinds of studies. And this lets us ask the question, how much of a difference could we make? And this is one of the rare things in psychology. We almost never give a specific answer. It depends, maybe. But here I can answer the question, and the answer is 0.47 standard deviations. On average, we improved spatial ability through training by almost 1/2 standard deviation. And I'd like to emphasize that this is a conservative estimate. This takes into account improvement in comparison in control groups. If I was going to design a spatial intervention course, there are many that have effects far greater than 0.47. But if you say conservatively, taking everything else into account, this is a conservative estimate. So how might training help? And I'm going to give you many different kinds of possible ways. Many of them have to do with increasing the basic capacity to remember objects, locations, and relations between them. And I'm going to give a demonstration, and I need to warn you this is going to move fairly quickly, so there won't be like a break. And you just have to, you're going to see a screen with a bunch of squares, and I want you to shout out the number of squares that you see. So get ready. Everybody ready? It's going to move fast. Okay. So focus on the X. Okay. How many did you see? How many there? Okay, good. That's the point. How many there? So I heard the correct answer of 9. There's a genius in the room somewhere. Probably a video game player. Then most people shouted out 4. That was easy. And this one's sort of intermediate. Okay. And what this is supposed to demonstrate is there's 2 strategies to doing this. For this one, it's called subitization. You just see it. And most people can do this up to about 5 or 6 on average. There's a second strategy, which is much slower, and that's counting. 1, 2, 3, 4, 5, 6. It's actually 10, but that's a pretty good guess. 2, 4, 6, 8, 10, but still almost genius. Here we have to count, and counting is slow, and therefore you can't do it. So you didn't have to count here, and you do have to count here. The reason I have this visual mask here is to wipe out your visual spatial memory so it can't carry over from trial to trial. Okay, Sean Green and Daphne Bevelare compared these two strategies of subitization and counting in people who did and did not play video games. And they found a really interesting difference. So this is how many errors you make, and then the errors start to go up above a certain number. For non-video game numbers, that was between like 3 and 4. That's because you start to have to count, and when you have to count in this very limited amount of time, you struggle, and people are inconsistent. That point of switching from subitization to counting is shifted for the video gamers. And they make the claim that this is actually a consequence of playing the video game. You should be saying to yourself, well, maybe people play video games because they're good at this. How do you know that the causal direction is from playing games to visual spatial ability? And from this one study, we can't know that, but they have done more experimental studies where they take people who are naive to video games and train them over several weeks to play the games, and we see analogous improvements. Not as dramatic, but we still see improvements. So the claim here is that playing video games is actually increasing the amount of relational information you can store in your fovea, and the center of actually the center of vision has increased. You can attend to more visual spatial information, and that range is increased. And it makes sense if you think about like a shooter game. You have to keep track of where you are, but also monitor surrounding space for possible incoming enemies. And so the combination of doing those actually seems to make a difference in visual spatial capacity. And if this is all you could do in STEM, if you're an introductory STEM student who's being bombarded with spatial diagrams, many of the students do describe the professor just started putting up all these diagrams that are supposed to represent 3 dimensions, and I just couldn't understand it. Sometimes she tried to teach me how to understand it, and I just couldn't get it. And this is like about 1/3 of the students struggle like that. And if you have greater visual spatial capacity, it might be that you can actually hold more information in mind before it fades. Okay, so that's the breaking point. So what are the results of the meta-analysis? That training was effective, that there were some cases where it lasted, and it also transferred. So as I said, the mean effect size was 0.47, which Cohen would describe as moderate. At the end of this section, I will tell you a little bit more about why I think that matters. It's equivalent of about 7 IQ points, which would make a big difference. Now, two things that are very important are duration and transfer. Duration is how long does it last? Because if the training only lasts for an hour, I can't make a claim that it could make any difference in STEM. However, for those studies that tested for duration, they actually found that the effect was maintained over time. In some cases, several weeks, in one case, over a year. It's important in analyzing these data to realize that this is a selected group. If you are going to train for delay, for duration, then you I know you use more intensive training. And so, yes, it can last, but it takes particularly duration. You could get a misleading result from just thinking, oh, there's no difference at all, but that's, most studies don't train for delay. Those that do find some effect. And likewise, we looked at transfer, which is whether it applies to another task. If all you can do is mentally rotate a block and you improve, and then it has no effect on anything else, then that's not going to be very effective for STEM. Now, transfer can be thought about in sort of degrees from very close to very far. let me say right up front that there's very little data for far transfer, which is by far the most important thing for STEM. So that debate is very much open. But for relatively close transfer, for example, mental rotation to another spatial task, or playing spatial games to mental rotation, there was evidence. Again, relatively few studies test for transfer, but those that did found that the effect did transfer. So there is at least an existence proof that transfer can occur. Mike will have a lot more to say about this, and I'll say more about it this afternoon as well. We know transfer is possible to tasks that aren't exactly the same. Whether it transfers to STEM or not is very much an open question. Okay, now, I'm always get asked about sex differences, and it is true that the following two facts are true. Women were on average a little bit worse at the beginning of training. That gap was closed, but not completely. So there's improvement in both groups, and I think that's the most important study, male and female, most important result. But it could be that all you need to do is some sort of threshold, that if we're getting people above a line, then they can perhaps get through introductory chemistry and organic chemistry, and that's what matters, not whether we completely close the gap. There are some studies that did find that they could completely close the gap. Those tended to be the most intensive training, in some cases the most boring, where you do mental rotation several times a week for several hours each time for several weeks. So you can close the gap, but it takes a lot of effort. Why does this matter? What difference would 0.47 standard deviations make? Well, you remember at the beginning I said that engineers, mechanical engineers, differed from the mean by 1.5 standard deviations. So you can think about 0.47 is only not even a third of 1.5, but if we think about shifting to distribution and we look at the number of people, the area under these two curves, we find that we could in essence double the number of people who have the spatial abilities that engineers do. So if you think of that as a prerequisite, then we're increasing dramatically the number of people who can fit under that curve. So it could in theory make a difference. So in theory it could double the number of people who are spatially qualified to be engineers. Okay, now let me switch gears and talk about the other approach of spatial thinking in context. This is much more consistent with sort of modern thinking about science education, that it needs to be taught about something. You can't just train abstract spatial thinking. We actually think both approaches have value. Here is the one for spatial thinking, and it's based on GIS, or Geographical Information Systems. This is not the same as the GPS that's on your phone. You can think of, in terms of spatial thinking, you can say GPS bad, GIS good. GPS doesn't seem to help and may in fact hurt people's spatial thinking. GIS is totally different. It's a system for representing spatial data. And it takes advantage of what maps do best, which is to help us think about relations. And it allows us to do it in multiple layers. So one you may be familiar with is Google Maps. You can layer traffic and satellite imagery. That's a very simple GIS. In a more formal GIS, you can represent anything that you have the data to represent. So in making, we talked to the business dean is here, in making marketing decisions about where shall I place a new business, or who should I try to reach in my advertising campaign, these decisions involve multiple dimensions, such as, well, what's the land like? What is it zoned, meaning can I use the land? If I want it, maybe I should put it in the old city, but there's no construction allowed there, or the streets are too narrow. And we have to make these compromises. Is it too hilly? Is the land already sold? Are there street access? Are there people with money close by? These are all the kinds of decisions we would have to make in making a complex, real world, in this case, business decision, but it could also be an engineering decision, where to put a new power plant or a wind farm or solar energy or whatever. These are the kind of problems that students will face in the world that they live in. So we've been looking at the effect of GIS training. which is becoming increasingly available and popular, and now in many high schools in the United States. This is one of the top 5 fastest growing jobs in the United States is geospatial analysis, because it does provide you a new way of thinking. How am I doing on time? Okay. Don't worry. Okay. So here are some examples in this course that I'm going to describe, which is called the Geospatial Semester. This is done in collaboration with Bob Colvard, who's Dean of Engineering at James Madison University, a large public university in Virginia. And he invented this course to sort of, as an alternative to high school physics, students who are taking the highest level, if they wanted to do something sort of more hands-on, nothing wrong with physics, but many of these students would take advanced placement physics, advanced placement chemistry. They instead could take this course as an elective, and it emphasizes geospatial reasoning. And as the course progresses, they learn to use GIS to solve real-world spatial problems. Now, this is a very local kind of problem. So these students are way out in a rural area near a national park, one of our first national parks, Shenandoah National Park in Virginia. And the geography of the park is such that it's kind of a narrow strip. And one of the negatives about that is that the bears can easily get out of the park. They're protected in the park, but then for food, they come out and eat from, like in this case, a bird feeder, or get into people's yards. This isn't particularly good for the bear or for the person. So the students were highly motivated to say, what do we do about this problem? Well, they take them back into the park, but what do they do? Where should we put them? And this is inherently a spatial problem, and they have to maximize a compromise between many different variables. So you want something as far away as possible, but there has to be a road that allows you to get there. You have to have a vehicle that's big enough. You can't just put it into the Baltic Taxi Toyota and take it up into the mountains. You have to have a fairly big truck, which requires a fairly big road. So these are all kind of compromises that they have to think through. And this student worked with the GIS and the data, which included where bears were found, where roads are located, where are the different bear populations. And the student identified particular places where he could recommend to the park rangers they should consider these are the best. If you find the bear here, put him here. If you find him here, put him here. And it seems simple, but it very much isn't. And he used this spatial representational technique to solve this problem. Here's a more conventional one where they're trying to decide where would we put a new restaurant. As you know, most new business ventures fail. Restaurants are notorious for this. You get people who love food and want to share that love with their fellow people. But unfortunately, most of the time, it doesn't work out. These are decisions that need to be made rationally and not just based on passion. It involves a great deal of information that is, hard to think about simultaneously. And so the mapping technology allows us to bring these variables together and do what maps do best, help us think about relations. And so they drew out where you could drive within 15 minutes. They looked at the distribution of age. If they're trying to attract young, hip people who are more likely to go to interesting experimental restaurants, then they had to have a population that had a car, that within 15 minutes, places to park, were the right age, and had the money that it would cost. And they could also look at projected population change. And actually what was interesting is that in this case, the student concluded that it was not likely to be financially viable to place the kind of restaurant he wanted to place in his hometown. And at least that was a good exercise for him. It may have killed his passion a little bit, but it saved him a lot of money and the failure of, going through this process. So this is very relevant for business because many of the decisions are spatial in nature. It's very relevant for, at least for American infrastructure, as flood after flood happens, and we have to think about where are we going to locate, where are we going to invest in in flood control, where can we afford it, where can we make the most difference. These are very much modern world problems. So the question I'm asking as a psychologist is, does taking this course affect spatial reasoning? Does it accomplish the goal that we set out, which is to make you more of a spatial thinker, not just to mentally rotate things, but to approach problems from a spatial perspective, to see old problems as new in terms of spatial data, to look for data and to represent it? And we're going to answer this question in a lot of different ways because there's no one single method that can show this. So we look at the answers to specific questions. We also count the number of spatial words that we use, and we score their final product according to a rubric that illustrates that assesses the goals of the course. So let me these are extreme examples, but in some ways they're representative. So we asked the students questions that required some degree of transfer, to think beyond a specific question that they were given in this class. So they were never given this question in class. This is not one of the questions they solved, but it is relevant. So what we're looking at here is, do they see this question as a spatial problem? Do they use the tools that they gave them? Again, we're not asking them to actually solve it. We're just simply asking them in a few minutes to tell us how you would go about solving this problem. And the problem is, if you were campaigning for local office, how would you run your campaign? There's nothing inherently spatial about that. So there are very reasonable answers that have nothing to do with spatial information, and I'll show you one in a second. This guy is in the class, and watch how spatial this question has become. Watch his gestures and such. Okay. This is a few years old. The answer he tried to instantiate this problem, he said, say I was for gay marriage, which is now a moot point because it's legal across the whole United States. But at the time, this was an ongoing political issue. And if it involved an election, which in the end it didn't because it was seen as a fundamental right, but he was saying, how could we win this election? And he's saying, we use a poll, and then we plot that out, and we target that area. Much like the marketing decision, but here they're not selling a product, they're selling a particular political campaign. And so you can see that he thinks about this in a very spatial way. So you could just see, this is a partial transcript. I would use probably something GIS related to find an area that would probably maybe suit like my platform. So he's seeing this immediately as spatial, and I'm going to use the spatial tools. I'd map out the poll data, I'd plot it, and I'd see where these things come together. These are some of the goals of the next generation science standards. There's a continuous process of educational reform in the United States, and the next generation science standards have been adopted by maybe a third of the states now, and they emphasize science as process rather than science as memorizing scientific facts. And so it's about doing science, it's about the practices of science. And these are some of the examples of sort of the things that people who have emphasized these new standards have said should be part of science. Constructing explanations and designing solutions, analyzing and interpreting data, engaging in argument from evidence, obtaining, evaluating, and communicating information. These are what they say are cross-cutting skills that are characteristic practices of science. And I really think this answer really demonstrates that he's doing many of these. He's seeing it as a data problem. He looks for the relevant data. He represents that data. Then he analyzes and interprets it based on the representation. Then he can make an argument about where I should do it. Now here's another student. The gender just happens to be, many girls did very well too. Now she's in the comparison group, which is students who are taking advanced placement physics or advanced placement history Most took both. So these are very high-level students in both the experimental and control group. So listen to her answer and watch her hands. It's a very reasonable answer. She says one of the things, I would get involved local businesses. This is a local issue. I'm going to go to the local influencers. She sees it as a problem of social network and not so much a spatial problem. You could argue that this is also spatial, but she doesn't actually say any of that. It's not a map problem. It's not a problem of distribution or representation. But I want to stress that her answer is a very reasonable one. It's just not spatial. I don't want to say her answer is worse than the first guy's. But you can also clearly see that the first student was greatly affected by the course. She hasn't had the course. And you also notice it in her gesture. Gesture is often a very strong sign of spatial thinking. She makes only one gesture, which is sort of like an emphasis point. It's not spatial, whereas the other guy was basically making a map with his hands to illustrate this is a mapping problem. So we really think we've affected their approach to problem solving. Okay, so this is the qualitative analysis of the answers to the question. We also used another kind of converging method, which is more quantitative, which it's very, very simple, but it reveals a lot. It's crude. I know we have formal semanticists here who would find this method almost disgusting because it treats the words just like a bag of words. It doesn't have anything to do with the meaning, but it's very simple. So this comes from James Pennebaker, who originally started this as a clinical psychologist, and he was known for having people keep journals, diaries of their experiences in therapy, and after a while he had hundreds of these, and he got tired of reading them. And he said, like, how can I make sense of all of this data? And he found out that people who were getting better tended to use words like happy, hope, optimistic, and people who were not getting better used words like sad, depressed, and he made dictionaries that were indicate, depressed or not depressed, and he found extremely high correlations between the individual clinician's reading of the journal and simply counting the words. And since the time that Pennebaker invented this technique, it's been applied to over 40 different kinds of questions. We applied it here to spatial questions, so we simply asked, do the students use more spatial words? How do we know what a spatial word is? Well, there were fortunately existing dictionaries, one from Pennebaker himself and another from these other researchers that emphasized more higher level things. So it's not just like right, left, but also shape and location and transformation. So we put these two together and we took the transcripts and we ran them through the computer and we looked at changes in spatial word use. Now importantly, we control for the amount of total words. It could well be that in fact it is, that students in the GIS group just talk more. These are more interesting questions, they understand what you're getting at, so they talk more. So that alone could be a confound, but it's not because we can statistically control for that. So what I'm going to show you is unique words. They only get a point if they haven't used that word before. So this shows the average number of spatial words used at the beginning, at the first interview before they've begun the class, and at the end. And you can see there's a really huge change, nearly double the number of spatial words that are used across the term in the GSS group, and actually no change or a little bit of decline in the comparison group. So they were very similar at the beginning and diverged greatly, and we think this reflects that they're seeing this more as a spatial problem and answering it in a spatial way. We also saw in the coding of their answers, we coded them according to rubrics that have been used in other studies of science education. This comes from Kate McNeil and Krajcik. And we looked at claim, evidence, reasoning. And again, we saw that the students in the GSS group made more stronger claims and better use of evidence to support those claims. So more evidence that it's making a difference. And finally, this is the most recent. This is still quite tentative, but the evidence is growing. We looked at neural evidence. This is with Adam Green of Georgetown University. And we used, one of the tasks is a syllogism task where you're asked these logical facts. The dog is left to the cat is left to the pig, is the pig to the right of the dog? So it's a logical thing. This is obviously spatial. This one isn't, but it's the same logical format. The dog is smarter than the cat is smarter than the pig is dumber than the dog, and then you ask another question. There's a big debate about whether people evoke a mental map to solve these. Here the answer is almost certainly yes, but here we don't know as much. And it does seem like some people see these non-spatial things, they try to form a mental map to solve them. And we looked at the consequences of participating in that class for how they solved it. And we found more spatial activation amongst those who had been studying the GSS than the non-GSS. So the syllogism becomes more of a spatial task at the neural level. And we also looked at some traditional spatial tasks. And one is the embedded figures task, where you have to try to find whether this figure is embedded in this figure. And we had some of them do it in MRI scanner, which is measuring blood flow to the brain, and selectively activated the posterior parietal cortex, which is involved with spatial processing. This is a very crude explanation of the neural things. It's very preliminary. But this is, to our knowledge, the first sort of neural evaluation of a natural class. So like most studies do some sort of intervention in the lab, but we think this is the first that's shown any kind of predicted effects at the neural level of a class in a regular high school setting. So we're excited about this, but it's still preliminary. Okay, so how does this work? What's going on? Just let me wrap up by what I think is going on. I think the critical thing that matters for spatial reasoning is that it gives you an alternate approach to the problem. So most students approach things from a verbal, semantic level. This is just the way we train Western students to think, and we have for 500 years. And I think, as Bob is going to show you, sometimes, though, visual spatial representations can give us an alternate perspective. And so when you're confronted with a problem that you don't know, if you don't, you can think about it and say, well, wait a second, what if I tried to make a mental image of this? Would this help? And so you're basically getting two chances. And it seems like the best people are the ones that can flexibly go back and forth between the two types of problem solving. And so training really seems to be as much about activating the possibility of spatial thing. Not necessarily you're going to solve every problem that way, but it's a second way of thinking about it. Because we don't educate it, people don't spontaneously do it, and training might help them do so. So to summarize, spatial thinking matters early in STEM education, but less so with increasing expertise. Spatial training works, at least for early on. It might make a big difference, but it's not all the difference. And part of this is a habit of mind that we're also trying to work on. So we need both the lower level approach and the higher level approach. So thank you to Jurgis and to the university and to Accenture for inviting me, and now I have time for questions. I don't know if I got the correct Universitātes Latvijas. Well.
Okay, thanks a lot. We have some time for questions, comments. Any questions? Okay.
Yes.
So the syllogisms which you did, like in the second example, I sort of naturally create a partial ordering. That's the first, but that's probably because I'm mathematically educated, or is this? You think it's more like the knowledge of the mathematical structure, or actually natural spatial reasoning there?
Well, I think that a lot of this is is the latter. It's learning about different tools of representation. For me, it's maps. Maps, you know, were invented by the Greeks, but then lost in the Dark Ages and rediscovered. And that discovery made a big difference in how they thought about the world. So I think partial ordering is a mathematical tool that you've been taught, and most people aren't taught these tools. So yes, natural ability matters, but probably not as much as teaching matters.
Thanks for your excellent talk. I want to return back to that example. You had those two students,
yes,
male and female. My question is, who was an interviewer? Was that interviewer the same for both of them?
I think the answer to that question is yes. So she's asking, do we have the same interviewer? We have two interviewers. I don't know in this particular case whether it's the same interviewer. Now, the way that we can address, do you understand, like we can't, it's impossible to have one interviewer for everybody because we had to travel and everything. So we tested for differences between the interviewers and we didn't find any effects of that. So overall, I don't think that made that much of a difference. Also, the interviewers had been in the classrooms many times and the students were generally quite familiar with the interviewers. But I also am very sympathetic with the general point of the question is that, you know, students may give different kinds of responses to different kinds of people. They may know what we're looking for. To really evaluate this, we need to look like a year later as to whether it's made a difference. We're evaluating, does it make a difference into what kind of jobs or colleges they go to? These are hard questions, but at least in the short run, it makes a difference.
So my point was, at least how I saw is that the guy who you showed, he's an extrovert, and the girl is introvert.
Oh, yeah.
And it doesn't really show, you know, those gestures. Not necessarily shows that was like spatial. That's what the gestures were about. That's what I was seeing.
Yes, and those personality factors could certainly matter. Overall, you know, we can't explain all the variants, but there is an effect of the thing that's above and beyond those things. But yes, those could certainly matter. And there are personality differences in how people respond. But the effects, there's an effect that's due to which class they took. That's not just that.
Any other questions, comments?
Thank you for the presentation. I was thinking about you are suggesting in your speech training spatial thinking at the college level, but have you considered or advocated for training it even at an earlier age for kids?
Yes. So this is a question of great interest to me, and it's almost ironic because almost all of my work initially was with young kids. There is certainly some work in training young kids and looking at correlations between spatial use and improvement in math. For example, kids who play more with spatial toys seem to do better in mathematics. So there's certainly analogous evidence. We focused on the STEM. You get this really interesting interaction at the higher level between cognitive abilities and domain knowledge. But it's certainly an interesting question at the younger ages too. I will talk a little bit more about that. I saved the developmental work for the workshop because that's more specifically focused on the problem of transfer. So yes, other people have. That was my very first study, was the effects of young children's map reading on spatial. So that's near and dear to my heart, not in this talk, but yes. Yeah. Well, come this afternoon. I know there's multiple workshops going on, and I don't want to advertise mine over the others, but these questions will be addressed. I had to save something for the afternoon.
Any other questions? Any other remarks, comments? If there are no other questions or comments, let's thank our speaker again. It was a really wonderful talk.
Thank you. Thank you.
Just a short announcement. So the next slot is a parallel session. So we will have a session in the large aula here. Then another session will be in a small